joining. Hello, everyone. Here we go. So we can go full screen right now. Here we go. Concept question number 5. Okay. Making sure you guys are awake. Showing you. Oh, that's also another good example of a simple machine, you know. That did happen a lot. That should stay. That should stay. So, look at the following diagram. If you release both blocks simultaneously from rest, which block lands on the ground first? Okay, well, hopefully we know by now, after watching the videos. I was going to say, is it A or B? So, block on the right will hit first, right? Because our radius is smaller.
I don't understand how it works. What's the equation for inertia?
Ooh, great question. Okay, so inertia. I don't have any pieces of paper. This is not good. This is an outrage. I'm going to use this one for now.
What is chemistry?
Wait,
Where's our color?
Trust me, you'd rather be learning this than what they're probably doing.
No, I already learned it.
What do they do?
I still think
Stoichiometry.
it's so easy.
All right. So there's my equation.
Yeah, those are the good old days.
Going grams to moles, moles to moles, moles to mass or molecules, depending on what you're doing.
I love that.
Right.
Me too. That's the best.
I'm trying my best. It's kind of a struggle, but yeah, if you want to do an escape room, I got an escape room for stoichiometry. So if you decrease the radius, you decrease the inertia, right? That's the goal. That'll make it move. Question.
So, if the radius is smaller, does that mean that the smaller inertia
Correct.
is like, I don't know how to put what I'm trying to say. Like,
The smaller the inertia, the more likely it's to move.
thank you.
Is that kind of?
Yes. That
Well-
is perfect.
Oh, can I rephrase that?
Yes.
The smaller the inertia, the more likely it's going to change its movement. So if it's at rest, it's more likely going to start moving. And if it's already moving, it's going to either speed up or slow down. Does that kind of help out?
Yes. That's why I was so confused.
Okay. So, we're good there? Perfect. Example number 5. Crushed it. Let's go to number 6. Oh, no, we're not. Let's go to 21. 21. Okay, small blocks. Small blocks, each with mass m, are at the ends of the center of a rod L that has negligible mass. Calculate the moment of inertia of the system about the axis. Okay. So, about the system. I'll start using Sharpie. I like Sharpies. Okay, so if we're looking at the system, let's draw it out. Okay, we got this. We got 2 masses, right? Looks something like that. Okay, so we're going to have 2 different inertia, and inertia. So we're going to call this I1, and we're going to solve for I2. So the first inertia, all right, so remember, it's my mass r squared. So mass. And then here, since it's directly in the middle, we're just going to have half of half the length squared. right? Half the length of the rod, I should say. Half the length squared. Does that make sense? Okay. So if you do this, that's going to equal mass 1/4 of the length squared. Does that make sense? So that's the inertia on this side. What's the inertia on that side going to be? The same thing, right? Okay, so inertia 2 is also equal to mass 1/4 the length squared. Alright?
Inertia can't be negative, correct? It's only positive.
Correct. 1/2 the length, that's L squared. Now, if we, remember, it's the sum of all that, so if we add those two together, okay, if we add those two together, our total sum is just, well, if you add 1/4 and 1/4, you add those together, you get 1/2 mass the length squared. I just moved my 1/4 up. Does that kind of make sense? Now try it for the point at 1/4 of the end. Okay, so the second part of the question, same setup, but the bar's here, and this is 1/4, and this is 3/4. Okay, so try that problem.
Why wouldn't you add like a M's to it?
Why would you not add
Yeah.
these?
Mm-hmm.
In this problem, you could have, I mean, essentially we kind of did at the last step. The next problem, they're being multiplied by different numbers so that you can't add those together. I mean, we are going to combine them at the way end, but you'll see. Bless you. Bless you. Okay, so those are the two numbers. This is a 9. Those are the two numbers I got. So when you combine those two, you're going to get M 10/16. 10/16 reduces to 5/8. That was great. Yes.
So if we were to see this on a test, like, do you want us to reduce or not? Like, does it matter?
I mean, I would always reduce if you have the option to. Yeah. Yeah.
Are we gonna have like a quiz or test over this before spring break?
Nope.
No. Okay.
Nope.
Thank you.
We'll probably honestly have a quiz.
Day we get back.
Oh, the day we get back?
No.
I was kidding.
I would cry.
No.
That'd be
We
interesting.
get back on a Tuesday.
Maybe a quiz over spring break?
I mean, if we're allowed to use our notes.
I mean,
Online school is always been, therefore it should be done.
All right. So, moment of inertia for different objects.
what the heck?
Okay.
Do you have to remember all of this?
Absolutely.
Are you serious? Or?
No. How would you? Do you see how
Don't
much?
scare me like
Do you
that.
see how many different equations we have here? 1, 2, 3. We have 10 different equations. 9.
I
Well, you know, some teachers would say it's an AP course, so
It is an AP course.
no, a couple teachers.
Surprise!
Okay. So just kind of how you kind of can actually see the different moment of inertias. Be interesting, actually.
We have no ideas. Look at him over there. He's gonna make us memorize all these equations now.
I mean, nah. We're not going to use all of them. Only 8 of them. I'm just kidding. Okay, so I just want you guys to see, like, there's a lot of different moment of inertias, right? Okay, looking at all of them. Mass radius squared. Pretty cool. Now, if you look at the spheres, if you start to look over here, or actually, let's start at the rectangle. So, if you find the area of the rectangle, you have a times b, all right? But then you got to square that, so you have a squared plus b squared, right? Times the mass, which is kind of crazy. So it kind of makes sense how each of these are figured out. All right, so when I give you guys problems, this is what I'm going to be doing. I'm going to give you the inertia equation because 9 equations, I'm not going to make you memorize 9. I mean, we've already used a lot of equations. I'm not going to make you memorize 9 more. So, most cases, if you look right here, I'm going to give you the equation that you are going to use. How cool is that?
That's pretty cool.
That is super cool. Okay? So, if we look, a torque of 12 Newton meters is applied to a solid uniform disk of radius 0.5 meters, causing the disk to accelerate at 5.7 radian per second squared. What is the mass of the disk?
Is the big M mass?
The big M is mass. Okay.
I was just making sure.
So that would be alpha, right?
So,
Because I was like,
Just to make
I was
sure.
too, I was like, what?
no, maximum's P, right?
if we are trying to solve this,
C equals MV.
and we're trying to solve this, okay? A torque of 12 Newton meters. Okay. So, I know my torque equation, right?
Length times something. Acceleration. Angular acceleration? No? Not angular acceleration. Sine of theta.
There we go. Force times radius times sine of theta. So, if we look here, my torque is 12. Okay, so I know 12. All right. Now, I know my radius is 0.5. And my radius is 0.5, so let's put that in. Sine of theta is just going to be 90, so we're good. Now, checking this out, force, okay? Force. Now, this is a little tricky one because are we given a force?
But
We're given angular acceleration, okay?
can you use
So looking at this problem, actually, yeah, I'm going the long way.
Sorry. right? I just said the wrong thing. That's L times.
I was definitely going the long way.
Right. I said the wrong.
Well, I thought it was length, not inertia, because I wrote an L.
Inertia, like property matter.
No.
I was definitely going the long way.
I wrote it down in here.
Wait, is this?
So here, 12 is going to equal my 1/2 m r squared. So r, which is 0.5 squared, times my alpha, which is 5.7. Thank you for the help. Thank you. Okay, so torque, inertia, this is all my inertia, 1/2 mv squared, that's right there, okay, mr squared, and then times my acceleration. So let's solve for mass.
Let's do it.
Are you doing it?
No.
Well, you said let's do it. 24?
That's the.
12.6.
Yeah, I got
Did you do 96 divided by 5?
Let's go, Andrew.
All right. We'll do it. We'll do it as a class. All right. So 12. We gotta divide this over.
1/2.
Divided by 5.7. Okay, so that takes care of that. I gotta times it by 2. Takes care. Divided by 0.5 squared.
Sorry.
I got 16.8.
Yeah.
Yes. Oh, it's
How do you do that?
Boom.
17. Which
How did I do it all? So first I divided by 5.7 on both sides. Right?
Yeah.
Got rid of that. So that leaves 2.10. Okay. Then I multiplied by 2 on both sides to get rid of this. Right? So that leaves me 420.
Then you divide by 1/4.
And then I divide by. Yep. Okay, cool. Let's try one more problem. One more problem. Find the cable's acceleration of the diagram to the right.
This is an outrage.
Where's our simple machine?
Where's our equation?
Definitely a simple machine. So, equation's up here for a solid cylinder, so 1/2 mr squared. All right,
That equal.
that's equal to the inertia.
Okay.
So here you're going to be finding angular acceleration.
The radius would be 0.06.
I'm sorry, say that one more time.
The radius is 0.06, right?
Correct. Let's switch it up.
Please excuse the interruption. Julian Owens, can you please come down to the receptionist desk?
Yeah, we're gonna go again for a second.
Oh, I got 0 points. You got 0 points? Did you get 6? Yeah, that's fine.
Okay.
Wait, what did you get?
I got 1.5.
0.6 or 0.0?
I got 32.
What?
No, I'm kidding. I'm kidding.
Oh.
I got it.
Okay, so let's kind of walk through this here real quick.
What is the radius?
So find the cable's acceleration. We're going to say find the angular acceleration. So find the cable's acceleration. So we know torque is equal to the inertia times alpha. Okay. Now, in this problem, we don't know the torque yet. Inertia is equal to 1/2 the mass. So the mass was 50. And we said the radius was 0.06 squared. So all of that's the inertia, correct? And then I got to times that by alpha, which I don't know. So I got to find torque, right? So I have to plug in torque somewhere. Well, I know torque, and this is what I was trying to do last time, is force r sine of theta. Well, if you looked at the problem, well, my force is 9. I know that. My force is 9 times the radius, which is 0.06, times sine of theta, well, sine of 90, right? Which is just 1. Okay, so torque here should have equaled, I got 0.54. And this is what you can plug in to there. Yes.
This might just be a completely dumb question.
No
but
such thing.
Does torque equals inertia times acceleration, is that like a set equation, like we use that for everything?
Yeah.
Okay.
I got it now.
I was just double checking.
It's 6.
Okay, so when you guys plug that in, yeah, 0.54 is equal to 1/2 times 50 times 0.06 squared times alpha. Ooh, that's terrible.
That looks like a
Nice.
slug.
Sine
Not a
is
slug.
There's alpha.
Hey.
So alpha, I think I got 6.
It looks like the stuff people put on the back of their cars.
Okay.
Yeah, exactly.
50 is one.
Can you go back to the picture real quick?
Picture, absolutely. So,
Okay. Yeah, okay.
so ladies and gents, real quick. Trying to keep this all, ooh, question.
I think I've gotten my six today.
When it comes to like the acceleration,
Yep.
That
like,
was
is it,
800.
how should we know, like, talk about like
I didn't
linear,
think so.
well, let's say like linear acceleration?
It should have said angular acceleration.
Okay.
Now, we solve for angular acceleration. If it just, how this is worded, I would go one step further and solve for tangential
Okay, so that's what I did.
acceleration. So if you did that, you just did this times the radius. Yeah.
We can't see it.
Oh. How do I stop that?
Control Z.
Oh, it stopped. Ignore all that coloring. But you would do this times this. So alpha times r is equal to acceleration. Right? So you got an answer that's 0.36.
Yeah.
And that would be meters per second squared.
Back to mindfulness.
So
Very
absolutely. Yeah, if it says acceleration, I would solve for this. Where if it said angular acceleration, I would solve for that. Very good. How do we feel on dynamics? Semi good? Good to move on tomorrow? Alright. We still got about 10 more minutes. You guys want to try one more?
No, we're good. We're good.
Good?
I think we should one more.
I think we're done for today.
If you guys are feeling one more, you guys, if you guys need a break, take a break.
That'd be nice.
But I'm feeling one more.
Mr. Bowers,
Yes,
do teachers have like spirit weeks too this week? Like,
I'm dressed up.
Are you?
oh, yes.
Do you know what today's teacher day is?
Collar and shirt day.
No.
It's like dress like a
Golf day.
No.
Christmas mask
dressed in
day.
high school day, or something like that.
Hey.
Yeah.
What is it?
Yeah.
That's how you dressed in high school?
Well, if I actually dressed like I was in high school, I wouldn't be allowed to. I wore gym shorts and a sweatshirt every
Why
day.
is this, then why is this a day?
Oh,
You can't wear that stuff.
I don't know. I mean, I was in high school 6 years ago, so. So like, it wasn't that long ago.
That's pretty ancient.
That's okay.
It's not like I'm dressing in the 80s.
I was in fifth grade.
Listen, I ordered my stuff 2 weeks ago on Amazon and none
Now I
of it.
could have a white.
That's unfortunate.
Yeah,
I graduated
it says it's not gonna come
2014,
until Friday.
7 years ago.
That's 2 years after my sister was born.
I didn't get one thing of it.
What?
2014.
Your sister was
I
fine.
definitely wasn't dressed in
Oh.
the
I have 3 of them.
I forgot.
8 years after he was working.
Other ones just don't count.
I would have been involved, yeah.
You don't exist.
8 years after he worked in Henry
Mr. Bowers, can we watch a goat video?
Like the goat video?
Yeah, we never finished it.
No, we did.
We got like halfway through it and it was about to fall, and we were like,
No,
oh,
we finished it.
did it fall?
Some of us stayed after the bell rang to watch.
Yeah, you gotta zoom.
Oh my gosh,
We should
please.
download Rainbow Six.
That'd be
That would be
hilarious.
so much fun.
I bought a gaming laptop last night, but I didn't.
I
I don't want to be crowded. That's what's building
I can't just bring a desktop to college.
You could.
I mean, I could, but I'm not gonna. I'm not trying to get it. I'm not, no. That's terrible.
Nobody's surprised. It has that.
We could do this.
Plus, I'm going to OU.
We could definitely do this.
We, Ohio University.
OU,
Have fun.
Ohio University?
Yeah.
Yeah, like this is tiny. And there's only one. But I definitely will be there to stay and graduate.
We could definitely do this one. I just felt like doing that. You guys got really quiet when I did that. Alright, so if we had.
Oh. Yes, we can.
I was
do
so
that.
close. Guys, leave the door open. Leave the door open.
I don't think they had fire drills back in the 80s.
This is tired.
Well, I was just outside.
The fire's shooting at us. I thought we did.
You were fast. That was impressive. Yes, go to wherever 10. Oh, so we're in 4-5 right now. Get your stuff. Go to wherever 4-5 will be. You'll probably be down there. An administrator will be.
So,
Go to 4-5.
okay, 4-5.
4-5.
Okay.
Guess what? Workshop.
Go to 4-5, guys. Have a great day.
Well,
Little extra
Yeah.
time in AP Physics.
I told you we wouldn't get to do that, bro.
Yeah.
Yeah.
we were hopeful.
Yeah.
Well, we said that we wanted to go outside yesterday.
Yeah.
You know?
What did you do?
I sliced my finger yesterday while cutting an avocado.
Fingers small.
When do you work?
Better get
Me?
30 Yes.
I work tonight, work tomorrow night. Friday day, Saturday day.
Okay.
No promises I might stop by.
That was so dumb.
I'd rather be outside in this class.
Thank you for your patience, staff and students, with the fire drill. We are going to be moving to 4-5 immediately. Students, once you get to your classroom, please grab your books and proceed to periods 4-5. You have about 3 minutes to get to your fourth period lunch or your 4-5 class. Thank you.
If you guys ever need a pass, just let me know. Teachers should understand. We were actually one of the first ones back in the building.
Have a nice day.
You too. We'll see you.
See ya.
That was not a fight.
I don't want.
Tommy Newman, can you come to the receptionist desk? Tommy Newman?
Oh no.